Friends, let's look at problem 131, palindrome partitioning. This video can be regarded as a continuation of our practice for backtracking. So we just look at problem 115.593, right? So for this one, actually the statement is shorter, but the requirement is different. So here we want to partition a string such that each of the substring is a palindrome. So we want to return all possible palindrome partitioning of S. So here the string has a length that is 16, right? And S contains only lowercase English letters. So this condition is crucial, right? So for each letter, if we consider the partitions, due to this number, so the number of partitions actually is quite not very large. So we can try all the possibilities. So this enables us to think of backtracking and bounding strategy, right? So our focus will be on how to design the backtracking code. So also we want to emphasize how we could use this condition. That is, every substring is a palindrome. So with that said, let's look at the two examples. The second example is very special because it's of length 1. So just the return itself, essentially. So for the first example, actually we can draw the discrete trees and the boundings. So we can use the first letter, the first two letters, and the first three letters. So this is the one level of consideration. So if you arrive here, you cannot continue, right? So this is not valid. Then we can continue to think, if we have used A, so then continuing, we can consider another A, right? And also we can consider AB, right? So this is another level around the first branch A, right? So this one is not valid. The reason is that AB is not a palindrome. Similarly here, AAB not a palindrome. So this is the first branch. So we get AA. And then if we can continue, we can have AAB because each single letter is a palindrome. So this is valid, right? So in other words, we get one that is AAB, right? So now if we look at the second branch, so we have AA. So then for the next one, we could only have B because AA is a palindrome. B is a single character. It's a natural palindrome. So we have another valid branch that is AA and B, right? So we have finished all the branches. So the return should be let's say AAB and AAB, right? So we return the result as a list of lists, right? So with that said, actually we can easily design a backtracking solution. So in this video, we are going to give two slightly different formats, essentially the same solution. Personally, I feel that the different formats of representing a code sometimes can be essential. For example, some people might be able to write a solution if using one format, but if using another format, it might have difficulty in writing a complete solution, right? So in the first version, I'm going to first call this length S. This is for convenience, right? And then I'm going to initialize a result list. So this is to hold all the possible valid splits, right? And then I'm going to initialize a split variable. So this is to be used to construct each individual split, right? So with that said, I guess one more thing we want to do is that we need to be able to check if a substring is a palindrome or not. So we can just write several lines of code within the DFS, the backtracking function. Let's see, DFS. So start from index, and then we are going to call this DFS function, and then we are going to return the result. But in between, I would like to write a individual function that is to check if a string is a palindrome or not. Here it can be a string or it can be a for example, list. So in the split, you can store it as a string, right? Or you can choose whatever format you feel convenient for you. So here I'm going to store something like A and B, right? Then, but for each of the ingredients we want, it's a string, so we want to check if it's a valid palindrome. So this is the main bounding condition, right? So this is rather simple, right? So let's first find the length, right? And then what we want to do is to check. We just need to check half, right? So for I in range, so m integer division by 2, right? So if the beginning ones, let's see, a string at the start does not equal to a string at the end, that is m minus 1. If you think of I equals 0, so the last index will be m minus 1. And then just here you just increment and here you just decrement. So you write minus I, right? So if these two do not equal, then we're going to return false. It's impossible to be a palindrome. After the for loop, if nothing has returned, so we are actually sure it's a palindrome. So this is a small hyperfunction, right? So with that done, we are ready to write the main backtracking function. So first, let's write the bounding condition. So if we are out of bounds, right, it means that we finished a split. So in this case, so we are going to add this finished split into the result. So what we are going to do is result append. So because later we are going to modify this split, so we are going to append a copy of it. So this will make a copy of this same for the current state, right? So we're going to add this. Or if you like, you can also try this, right? This is also good. So here I'm going to use this one because it's more convenient. So I'm going to return. This is the bounding condition. So next, we can, like here, we can try the first character, first 2, first 3, as long as it's in bound. So basically, for I in range, so starting from the current index and the end the last one. So then the substring we are going to consider is nothing but S. So start from the start index, ending at index I. So we write I plus 1, right? So so if this guy is not a palindrome, we are not going to continue along this branch, right? So basically we need to check. If check to consider. If this is a palindrome, then we can do the following, DFS. Because we have used letters up to I, then we can go on to next, that is DFS I plus 1. So here actually I forgot one thing, because we want to use this to consider. So we are going to do split append to consider, right? So after we explore the current branch, so we are going to do a pop to recursively go back to the previous states, right? So this, if you understand as advanced step, we're going to move to the previous state. In other words, before we consider this to consider. If you think it in a recursive way, actually we return to the previous steps. So this is our main DFS function, right? So afterwards, so you just call this function. So I'm starting from 0. So you can understand this DFS function as a worker. It does two things. First, it builds the splits, and then build this one. And once it finishes a build, it's going to add the build to the result, right? So then we just need to return the result stage. So this is the one format of a solution. So we can try. Yeah, it passes the first example. The second example is sort of trivial, so we can do a test. it passes all the cases. So this is the one format. So for some tweaks and tunes, I'm going to copy this code and write another form, right? So here, I guess one thing is important to emphasize, and it's important to append a copy of the construction of split, right? Otherwise, you're going to mess things up. So this is the version we want. So for the second version, what I'm going to do, I'll keep this part. I'm going to put this guy into the function signature. So let's cut this and put it here. So this, we use it as a keyword argument. Notice that this is a list. List is mutable, right, in Python. What we are going to do, so here, actually, because each time we are going to put a new instance if it's different from the empty one, so we can consider to just put append split. So when do return, then here, after we check, we don't need all those actually, right? So if it's a valid palindrome, so what we are going to do is, so still I+1. So however, here we are going to modify the split to be another new instance of split, but we add the current to consider, right, to the result. So then we just need to call df_0 because here this is a keyword argument, right? We don't need to be specified because it has a default value. So with that said, I guess we can test this version. It passes one example. Now let's look at the generic case. Yeah, it passes all the cases. But if you want to make sure this is the copied one, you can put a copy for sure. It will work, right? But it's sufficient to just use the split itself. So with that said, I guess that's about it for the coding part of this video. So to summarize, so we give a backtracking and bounding solution for this problem. So here we presented two formats of the same solution. So one is that we use we isolate this constructor for each individual split and then add to the result. Another one is that we put the constructor of the split into the function signature, and then each time we pass the argument to the function, so we actually pass it a new instance, right? So this is the difference between here, I put it outside, and here put it in the function signature. So actually, it's important to pay attention to these small details so that you can freely use whatever format you want, right? So with that said, I guess that's about it for the current problem and the current video. Thank you.